Welcome back, everybody. This is about to be an absolute banger of a video. Today we are taking a look at what a logic gate physically looks like. I was taking a CMOS course in WashU not long ago, and what we had to do was design a logic gate out of transistors, which that alone is a whole career. But then we had to implement it into what's called a layout. Now, I've never heard of what a layout is, and then it wasn't until after the fact that I found out, and it just opened another world. As soon as I thought, I would be done talking about logic gates, here we are. We're back on logic gates. And to be quite honest, I can't think about any better topic to make a video about than, well, I've got another video planned, but making a video about the concept of a layout is definitely something worthwhile. So, yeah. But before I get started, I want to mention a couple things here. Over the past 2 years, 2.5 years, give or take, I've been very busy with my day job, and I've started getting into other hobbies and activities outside of work. So that's been taking up a lot of my time. So I've sort of neglected to upload YouTube videos. I'm not going to say that I neglected my YouTube channel because I'm not really maintaining it as well as I could. I'm just, my focus is not my YouTube channel. But nevertheless, I am excited for this one. Okay, so CMOS design, right? Let's write it out here. So what we have here on the left is we have an NMOS transistor, and then we have a PMOS transistor. What you'll notice is that there's a little circle here, and all that really means is it's indicating to us that PMOS has an inverting nature to it. So whatever input goes in is treated like the opposite of that. Another important thing to note is that for your designs, for every PMOS you must have an NMOS. So the number of PMOS must be the same as the number of NMOS in your design. And so that's where this word C stands for. It stands for complementary metal oxide semiconductor, CMOS. Additionally, we need to be familiar with De Morgan's law. If you're not happy with these equations, this video might be a little bit too advanced for you, but as far as you take my word for it, you should be fine. But I strongly encourage anybody who wishes to understand digital design to really prove themselves, how these laws work. I've gone through the proof myself. I've done it myself countless times already. But it is a good thing to do in order to move forward in your studies. Okay, so let's just move on. Let's go straight into the inverter. Now, there's a lot of things going on in this picture, but let's start with the leftmost, right? The symbol for an inverter. It is a simple triangle with a circle at the end of it. Circle right there. What this means is basically anything that come in, you can expect the output to be the opposite of what came in. So we have our truth table here, and it describes that behavior. So 0 in is a 1 out, and then a 1 in is a 0 out, so on and so forth. Let's see what that looks like as far as the transistors. On the top, we've got a PMOS transistor, and in the bottom, we have an NMOS transistor. So let me change colors. Let's take 0, for instance, right? Let's pretend 0 is coming in. As far as the PMOS transistor is concerned, this looks like a 1, so it's gonna, short it. So it'll allow current to flow through. When it goes to the NMOS, it's gonna act like an open circuit because it's a 0. All right, so this is an open circuit. So what that means is our output will approximately equal VCC. All right, or we can just call that 1. So very basic stuff. Okay, so that was the basic overview of the transistor, explanation of the inverter. Now let's move on to the layout, right? Just bear with me for a second. Let's just look at the yellow rectangle, and then let's say that is our PMOS, transistor, and then let's look at the green rectangle, and let's say that is our NMOS transistor, right? And the intersection from the red rectangle and the yellow rectangle, that's what we care about. That is, the PMOS transistor, and then the intersection from the red and the green rectangles are the NMOS transistor, right? So let's write it out. So there is a lot of physics behind this here. So for instance, right, if you want to know what your voltage threshold is, right, it is a measurement of when your inverter goes from the, I guess, linear region to the saturated region. And one of the important parameters, to that formula is going to be these distances. So this distance here, and then this distance here. This is the length, and this is your width. These are very important parameters for your voltage threshold. But let's not really focus too much on that here. For our sake, all we need to know is that that's where our transistors are located. And the important thing also is to make sure that we are labeling our source terminals correctly and our drain terminals correctly as well. So if we look here on the transistor side, right, we can label these things here. There's our source, here's our drain, and then here's our gate for the PMOS transistor. And then if you look down here, there's the drain, here is the gate, and then here is the source for the NMOS transistor, right? So we can see the equivalent terminals on our layout as well, because I've placed my labels on it, so as to not confuse me. So here's the source, and then we've got too many arrows going on here. So yeah, there's a source, and it's connected to the VCC, just like in the transistor. And then here's the drain, and it is the output, and it's also connected to the drain of the NMOS transistor. So that's just, one straight line from here to here, like that. And then likewise with the NMOS transistor. The NMOS transistor's drain is connected to the output, and then the source is connected to the ground, much like here. Much like it is on the transistor side here. So that's really what you need to know as far as the layout. Okay, so the last thing I want to mention about this is the gate connection, right? We have an input on the transistor side, and it's connected to both gates of the PMOS and the NMOS transistor. And likewise, we have that situation here on our layout. The only difference is that we're not really drawing a line in the middle. We're just hooking it up like this. We're drawing here and then just, making a dot there to, let the audience know that, hey, this wire is connecting. So moving on to the picture that we have here. This is what it actually looks like in the simulation tool. And when you get to the point where you can start manufacturing your inverter, this is basically what you're going to give them, right? And when it gets manufactured, it's gonna look like this. So if we look at it, I've labeled it. You've got the VCC here. It's at the very top. We have the input, which is at the gate. I guess if I were to draw it, it would be here like this. Now, it doesn't matter that like my input is like, turning left and right here. What matters is that that's my input, right? Because that at the end of the day, that's just a node in my circuit. And then we have a ground at the very bottom. And we have the output, which is, I guess it's a wire that connects both of our drains. The drain of the PMOS and the drain of the NMOS. And we can also see some interesting things here. We see these dark squares here. Those dark squares just symbolize to us some, what's called contact pads. So a particular material is, in contact with another material that is overlapping it. And so that's how this works. It's like different materials are overlapped upon one another. I have another picture, but it's actually the same picture, but over here I'm explaining a little bit more as to how these layers work. So we will see that for the top portion of this layout, we have like an N well, and then in that N well we place a P active region and an N active region. I am still not entirely sure why we place an N active region in our PMOS transistors, but what's funny is that I don't need to know the reason for that, and I was able to design an entire like encryption circuit without needing to know that, as long as I knew how to wire up the rest of my circuit, I was fine. Okay, so I went ahead and I drew an extra inverter to the side of it. And so let's just say, for instance, I want to wire up 2 inverters in sequence, right? So if I take my schematic, it'll look like something like this. Bear with me here. So a line. Like that. Let's say I want to make something like that. So it's going to be very straightforward actually, and I've already started to draw out the rest of the or the first set of transistors. And what you'll notice is that I extended out this metal here towards the other side, and likewise with this side here. That allows me to share. Well, it is the best idea to have one VCC, right, or one voltage source, and allow for both inverters to use it. So, and the same for ground, right? I want both inverters to use the same ground. So it's just a matter of extending out this blue metal and allowing the other one to use it. So if I were to draw out the same thing that I have on the right, it would look like this. So right now I'm just drawing my contact pads, right? And when I draw the blue rectangle over it, what that means is the contact pad is going to connect the P active region and the metal together. All right, so let me redraw this red rectangle, in fact, to make it more neater. Like that. And then let's draw the metal. Just like that. And then finally our input is going to look like this. And then we'll have some contact pad here that connects the metal type 1 with the poly metal. Oh, and let's not forget, see, this is the importance about, making these circuits, is you can't miss anything. And the reason there is no contact point here, you'll notice, is because, well, it's the same type of material, so they'll just naturally connect. And then if we want, we can draw a pad here, that basically indicates that this is the input, and then the pad here is the output, right? So let's call it input, and then we call it output. And there you have it. You've got two inverters in series, and this is what, it'll look like more or less. Okay, so now we have that concept out of the way. We can start to go, more into logic gates and not just an inverter. Notice we spent a lot of time on an inverter, but it's really important to set the foundation. So the next thing we want to do is a NAND gate. All right, so now we're talking. All right, so like we did with the inverter, let's start with the leftmost part, which is the symbol. And you'll notice, why did we start with a NAND gate? Why not a AND gate? And well, it is actually easier to make a NAND gate than it is an AND gate. It's a little bit of a mouthful, or tongue twister, I should say. But let's look at the Boolean equation or Boolean expression for an AND gate. So we've got the output is equal to A times B inverted, which is the same as A inverted plus B inverted. Now this follows De Morgan's law, right? And if you look at the truth table, it's very simple, basically it's the inverted version of an AND gate. So 0 0 is 1, 0 1 1, 1 0 1, but then 1 1 is a 0. So yeah, so let's see if we can make sense of this here. So let's look at the example. Let's look at the second example here, right, where A is 0, B is 1, right? So let's say A is 0 and B is 1. All right, let's place this down here. So it's going to be the same here, right? Because this is also A, and then B is 1. So we have a short circuit on the left side. So we have current flowing freely here. But then this side here on the right is an open circuit, right? So no current here. On the bottom here, we have a closed circuit, right? Because current cannot get through here. And so now the following transistor B, well, I guess we don't care. So now the output, I guess there's something missing from this picture. Like, what's missing is, where does the output come from? Well, it comes from here. So in this example, we can expect the output to be a 1. Okay, that's cool. Well, let's consider the example where A is 0, A is 1 and B is 1. Okay, so let's clean. Okay, so we're looking at the example when A is 1 and B is 1. So it's basically this scenario here. What are we expecting? We're expecting a 0 on the output, right? So if we have 1 1 on the PMOS transistors, then there is no current flowing through, right? So no current. Like that. But we do have current flowing through the NMOS transistor, right? So current flows freely. So basically our output is connected to ground, and well, we know that as a 0. All right, so that's the gist of the NAND gate here. All right, and let's move on to the layout. All right, once again, we have intersections of the poly material and the P region, as well as the N region. We've got 4 transistors in total, because we can look. You see that there's 1 intersection, 2 intersection, 3, and 4. So that indicates to us that we've got 4 transistors. Let's take a look at the terminals, make sure they're correct. So for both PMOS and NMOS, right? Let's put the labels on the transistor side here. So we've got the source on top, gate on the bottom, gate here, and then drain going to the output, and we can see that there is a bit of a flip-flopping as far as the the drain and the source terminals, but as long as we're consistent. So in other words, we've got a connection right here, and it's coming down, it's going over this wire, and then it's hooking up to the drain of the other on the other side, which is the PMOS, or NMOS, and that is our output, right? So essentially both drains of the PMOS transistors are hooked up to a single drain of one of the NMOS transistors, right? So we've got a drain here, we've got a source here, and then a drain here, a source here, and then a gate and a gate. So what we'll notice here is that the source of transistor A is connected to the drain of transistor B, and that is exactly what we have here. The source of A is connected to the drain of B. So we can tell that our transistor A is located here, transistor B located here, and likewise with our PMOS transistor A is here, transistor B is here. I mean, technically you could call it A sub 1 and then A sub 2, but you get the idea. Okay, so moving on. This is what the layout looks like, the physical layout. We've got our voltage source right here, this whole metal. Our ground right here is this entire metal here. Our output is starting from here, and then it's connected to something to the right. And then our input, technically I guess I could draw some metal here like that and like that, and so I can redraw these inputs here. I can say that A is right here, and then B starts right here. So that is how this works. Alright, so let's think about this. What would the AND gate look like, right? If I've got this truth table and I want to create a AND gate, all I need to do really is place an inverter on the output here. So I would have to place an inverter on this side right there. And what would that look like? Well, you guessed it. It looks like that. And so once again, we've got our truth table. This time, we all know what the truth table of an AND gate looks like. And if we move to the layout, we see that the inverter is separate. That's because we don't want them to share the same, we don't want to share the drain or the source together. The only thing that gets shared is the voltage source. And so the voltage source, we want to hook it up to the source of the inverter, the same as for the ground. So technically we can actually combine these two here, now that I look at it like that. But perhaps in your design you saved a file where one file was the inverter and then another file was the NAND gate. And so you can put them together, but you just need to remember to hook up the the voltage source and the ground correctly. So yeah, I think this is a good example here. So if I have the P region connected to the inverter from the NAND gate, and then the N region connected to the inverter, like this, right? I'm talking about like this connection right here, and then this connection right here, and then we don't need the voltage source to be connected here like that. You just delete it. But the way it works is you'll have the inverter saved as a file, right, in your simulation software, and then you'll have your NAND gate also saved as a file. And in those files, you'll have the layout representation for both, for what it is that you have that file saved for. And so in this case, your inverter won't be, it won't be spreading out, to the left. So for instance, in this case, right, if we look at this piece of layout, this is the file. Let's draw that line again. This is the file I saved for my inverter, right? And I don't necessarily want my P active region to extend out this way, because what if I don't want it to touch to anything else? So that's why it's saved like this. But there's nothing stopping you from doing it, combining those P regions. If I could just clean this up here. So like I said, there is nothing stopping you from hooking them up. It's just a matter of your design practices. So yeah. So right here, if I can draw it out too here, right? So I can create another file. In fact, right, this is what's so interesting about this. I can create another file and I can call it my AND gate, right? And so in that case, then I would start optimizing that specific file. Some things that I would do is probably like move the entire inverter to the left here. So I would probably, take all this and just bring it over to the left a little bit, because I see some space that is not being used here. And then the other thing I would do is I would connect these two P regions, as well as connect these two N regions here. And then I save a little bit of space. And but the interesting thing is that I did not use the AND gate all that much, so I don't have one saved for it. Or rather, I do have an AND gate saved, but I did not optimize it. So yeah, it's an interesting problem. It's not really a problem, but it's something to be aware of. Okay, so let's move on. So we've covered quite a bit. We've covered the inverter, the NAND gate, and the AND gate. So the next logical step here is the NOR gate. So once again, we have a NOR gate, and then we've got the De Morgan theorem here. There's our truth table on the bottom left, and then there's our transistor circuit. So you notice that our PMOS transistors are now in series and our NMOS transistors are now in parallel. It's basically the opposite from the NAND gate, and I find that fascinating, but it's just how it works out. So I guess let's just look at one example. Let's look at the example where both A and B is equal to 1, right? So we've got a 1 here and then a 1 here, and right away we can tell that, okay, well, that is just gonna create some open circuits here and then some closed circuits here. And so right away we can see that the output is going to be a 0. The only way that we can get a 1 out of the output is if we have 0, 0 here, because we want the PMOS to be basically turned on. So we want to turn this one on for a short circuit, and then turn this one on for a short circuit, and therefore the output will be 1. Okay, so that's not too bad. That's not too hard to understand, in my opinion. This is what the layout looks like, and I did something a little different with this one. I brought in an example from a Wikipedia page. This is an example of another kind of styling of the NOR gate, and what you'll notice is that they have a smaller P region here, and then a smaller N region here. And so technically you could, you could customize this quite a bit, as long as you're consistent. And the other thing that they have is several contact pads from the metal to the P region, and several contact pads here from the metal to the P region that goes towards the voltage source. And then these two contact pads connect to this metal, which then goes to the output. All right, so, some of you might look at this and you say, wait a minute, something seems off here, right? On my layout, I've got the drains hooked up right here in the center, which then goes to the output, right? So if you look back at our transistor, we have a drain here, and then a drain right there. So we can see that they connect to both drains of the NMOS connect to one drain of the PMOS, and so that all connects to the output, right? But this one's a little bit different. This just has this area here goes to the ground. Well, in this example, they said, all right, this area is not going to be our drains. This area is going to be our source. So they said, okay, here's the source, and then here's our drain, right? And then the other thing you'll notice is that they used a different metal. So now they've got this purple metal, and it is connecting this area. So I guess I can draw it out too, right? They've got this metal is connecting to this metal, which then connects to the output. And they have these two sources hooked up to this contact pad, which then connects to the ground. So it really doesn't make a difference. You'll see that my two sources here, this one and this one, are also connecting to the ground. So I went ahead and I drew the layout to be similar to that of the picture that we have. And so I'm going to make the claim that these two are equal. In fact, all three of these are basically equal. As far as the simulation software is concerned, this is all the same. And of course, let's not forget we have input A and B right here. And it's actually labeled out for us too, which is nice. And one last thing I need to mention is that they have these purple contact pads. And so this allows you to connect to the blue metal. And then the other contact pad allows you to connect to the poly material. So everything is consistent. So now we can move on to the OR gate. And in this example here, I'm not even going to bother to create the layout. Well, the truth is I don't have a file for the OR gate. I have a file saved for the NOR gate because I use that one, but not this one. So yeah, the OR gate is just the same as the NOR gate, except it's got an inverter in the end. And once again, we've got the layout here. All right, so let's just keep moving on. The next logic gate that I'm going to look at is the exclusive OR gate, and we're going to have many more transistors on this one. So let's take a look. This is what it looks like. One thing that I failed to mention is how these Boolean expressions translate to the schematic. And it is true. I did not explain to you how it works. But the beauty of this is that you're just going to have to trust me on this. This is how it works. All right, fine. I'll give you a quick rundown. So when you're given a Boolean expression of any kind, you want to put it in a form that the entire term has the line over it, like I did right there. Once you have that, you can then create the NMOS equivalent of it, right? So this transistor schematic, we can divide it into two. We've got the top here, and then we've got the bottom. And these two schematics are complementary of one another. So we'll see that A is adding with B. So what that means is, or negative A is adding to B, and then they are multiplying, which is, I guess, that's a series. And it's A in parallel with negative B, or B naught. So we have two transistors in parallel in series with another two transistors in parallel. So let me just say that verbally. We have A naught in parallel with B in series with A in parallel with B naught. So, all right, that's what that looks like right there. And so my B is a little bit messy here, but B naught like that. So the interesting thing is how we handle these negative numbers. So we're gonna have to use two inverters to handle this. So let's already imagine what our layout would look like, right? You would have a set of inverters on the left, followed by the actual exclusive OR setup on the right. So let's go to here, and that's exactly what we have here. So the leftmost inverter is, it inverts the A signal, and then the rightmost inverter inverts the B signal, followed by the actual exclusive OR. And so I've also gone ahead and labeled each of the gates here. So we've got B naught on this side, and A, and then A naught, and B naught. So it's goes back and forth here. So let's look at one example. So we've got on the PMOS side, right? So the top side, we've got the source. We've got two sources connected to our voltage source. So let's see what that looks like here. And that is basically what we have here. Well, this is VCC, right? Is that what I called it? Oh, I called it VDD. Okay. Let's go back to VDD. And then we've got the drain of A is connected to the source of B naught, and then the drain of A naught is connected to the source of B. So let's see if we got that here. So right here, the drain of A is connected to the source of B naught, like right here. So they're basically in the same area. Let's delete that. And then the drain of A naught is connected to the source of B. So that's right here. So, so far it's consistent. So far it's good. Let's look at another example. Right here, this one. So we've got the source of A naught and the source of B is connected to the drain of A to the drain of B naught. So this connection right here, right? What does that look like as far as the layout? So let's go to it. And there we can see it. I'm going to go ahead and draw with a blue line here. Basically it's a single node, but it connects 4 components. All right. So right here we are up to 3 components now, and then we go to the final component now. We are at 4. So that one line connects the 4 NMOS transistors. And just to reiterate the point, all NMOS transistors are located here. Okay, so what does our actual layout look like? All right, so let's take a look at this. trying to get rid of the blue marker here. There we go. So let's take a look at that one more time. And then let's move on to the layout. In fact, I have a little surprise here. I have the layout and I have the actual simulation of the exclusive OR gate. So here's what the layout looks like here. It doesn't look too bad. Right here. And so the middle circuit is my simulated circuit here, and I did this one. I did this process for all of my components that I made. And then on the left, on the bottom left, we see a timing diagram, and that just proves to me that the exclusive OR gate is working as intended. So the way I like to understand this is, if they are different, you have a 1, but if they're the same, you have a 0. So that's, a simple way to understand the timing or the truth table of an XOR gate. And so we expect that behavior on the timing diagram here. And so the bottommost signal is the output, and then the top two are the inputs. And so when they are equal, you can see that it's 0. So right here, you can see that the output is 0. And then when they are different, so in this case B is 1 and then A is 0, and so the output is 1. So, that's working pretty well. All right, and then last but not least, we will move on to the negative edge triggered D flip-flop. So notice I said negative edge triggered, so that means, right, you've got a timing diagram, right? And then we have our clock. So I want my D flip-flop to react to the negative edge of the clock side. So I want it to react to this specific side. Or I guess we can call it the falling edge. So I want D to change only here, right? I don't want D to change anywhere else. And this is just an example of what that might look like. So it could, be any value really. Okay, so this is what the symbol of our D flip-flop looks like, and then our input is D. And based on the clock and based on the current state, we will have a brand new state, which is the, we call it the next state. But yeah, the input essentially sets the value for Q. And so if you've got a 1 for the input, and then your clock triggers, and then your next state is going to be a 1. And then likewise with 0, right? If you got a 0 in your input and then your clock triggers, and let's suppose that your current state of Q is 1, and then you've got a clock trigger, then your next state is going to be 0. So, well, actually, I just circled the negative Q, right? Not to be confused, right? The current state and then the next state are two different things, right? So then your current state is 1. Well, that just means that your 1 is going to be converted to a 0. So I guess these two are just the opposite of one another. And sometimes it's useful to have like the negative signal of your output. So that's one of the benefits of having a flip-flop too. So let's move on. And so the reason we want to control, the reason we have the master latch and the slave latch is because we want to control which edge, our flip-flop is triggered on, right? If we didn't care about the edge, we would just have one latch. But in this case, we have, two latches. If we wanted our D flip-flop to trigger on the positive edge as opposed to the negative, then we would simply add another inverter here. But that is not the case. Okay, so this one is going to be a tough one because we have to create a layout of these NAND gates, all right? And let's quickly go back up to the NAND gate, see what that looks like, right? So there was about like 8 of those, right? We're going to need to have 8 of these in one layout. So let's go ahead and go back to it. So this is what it looks like. All right, it's quite a bit, but you know, it all makes sense and it works. I've tested it, and this is what the actual physical design will look like. And I just want to remind everybody that we're just getting started here. Like, we're not even to the point where we're combining multiple flip-flops and, you know, creating elaborate circuits. That's going to be in future videos, but this video is to just show you how you can go from, you know, simple transistors to physical designs right here.